In this last video, we will explore the conditions in which there exists a unique solution for our optimal model parameter, theta. But let's take a step back for a second. Let's consider, the modeling problem in general, where we have some model and we are trying to determine the value of theta that minimizes average loss across our data set. And, of course, that value of theta is our optimal model parameter. Well, the loss functions that we've looked at so far, squared loss and absolute loss, both are always greater than or equal to 0, right? It's impossible for, something squared, if we are dealing with real numbers, to be less than 0. And similarly, the absolute value of something is also greater than or equal to 0. This means that the mean squared error and mean absolute error are also both greater than or equal to 0. And so intuitively, what I'm trying to convey is that there's always some value of theta that minimizes our average loss. The thing is, there could be multiple. And so let's consider the combinations of models and loss functions that we looked at before this lecture. The very first model we looked at was the constant model, and we looked at the squared loss, and we determined that the value of theta hat in that case was the mean of our y values. Now, as you know, any set of values has a unique mean. You compute it by adding up those values and dividing by the number of them that exist. There's only one possible value there, and so the constant model with squared loss has a unique optimal parameter. And now, there's a reason I'm looking at these not in the order that we presented them, but in this specific order. We also looked at the simple linear model with squared loss, and we found that the optimal model coefficients are these: r sigma y over sigma x, and the mean of y's minus theta 1 hat times the mean of x's. Now, given two sets of values, their means, standard deviations, and correlation coefficients are all unique. So once again, for the simple linear model, the optimal model parameters are unique. Now there's a little caveat to that. If either your x values or your y values are constant, so they don't change at all, the correlation with a constant is actually undefined because you divide by the standard deviation, and the standard deviation of a set of values that are all the same is 0. So there's a little murky territory there. But we almost never try and fit a linear model with one of our values being constant. So that's not really something you need to think about. We also looked at the constant model with absolute loss, and we saw that the value of theta that minimized average absolute loss was the median of our y values. And so this was unique when there was an odd number of y values, but you may remember at the end of that video, we looked at a little example where we had an even number of y values, so an even number of observations, and it turned out that there were infinitely many solutions for theta that minimized mean average error. Any value that was between the sort of middle two values when we had an even number of observations minimized mean absolute error. And you can go back to that lecture video if sort of what I'm saying right now is a little unclear. But my point in bringing this up is that there doesn't necessarily need to be a unique solution for the optimal value of theta. And so with that, let's take a look at our optimal model parameter that we've sort of been discussing today. We saw that theta hat is equal to x transpose x's inverse multiplied by x transpose y. Now, if you work out the dimensions of this multiplication, you see that x transpose x is a matrix of dimensions p plus 1 by p plus 1, and x transpose y is a vector of length p plus 1. And so if x transpose x is invertible, the way we compute theta hat is by this formula. But this solution for theta hat is really the same theta hat that satisfies the normal equation, which we mentioned earlier. And you can interpret the normal equation as being a sequence of p plus 1 equations with p plus 1 unknowns, right? So each of the p plus 1 equations are sort of the rows of our x transpose x matrix, and the value for each of those equations is x transpose y. And so our optimal value of theta hat, is the solution to this set of equations. And so, as we will see, it is possible that this set of equations doesn't have just one unique solution, but rather has infinitely many solutions. And so, when does the unique solution exist? A solution exists, generally, because, given a set of points, we can always draw a line of best fit. There may be multiple equally good lines, but we can always draw one, and so a solution always exists for this specific case. A unique solution exists if and only if X transpose X is invertible. If X transpose X is not invertible, we can't use this expression to compute the optimal theta hat. And so it turns out in that such a case, there will be infinitely many values of theta that minimize average squared loss. The issue with that is that they all have different coefficients, and it's not really clear to us which one we should use for building our model. And so that's a case that we want to avoid. We always want to try and put ourselves in situations where there is a unique solution for our optimal model parameter. And so let's discuss when X transpose X is invertible. So I'm going to walk through a sequence of arguments, and these all rely on a pretty deep understanding of linear algebra. So feel free to post on Piazza or take a look at the resources about linear algebra that we've posted if you aren't able to follow one of these steps. Well, X transpose X is invertible if and only if it is full rank. Now, as we looked at earlier, the shape of X transpose X is P plus 1 by P plus 1. And invertibility is only defined for square matrices, right? The rank of a matrix is equal to the number of linearly independent columns that it has. One of the, sort of big properties that you look at in a linear algebra class is that the number of linearly independent columns that a matrix has is equal to the number of linearly independent rows that matrix has. And so the row rank and column rank of a matrix are always the same. Another property is that X transpose X and X both have the same rank. Now, once again, the proof of this is beyond the scope of this class, but if you're interested, you could prove that both X transpose X and X have the same null space, and you could look at the rank nullity theorem to arrive at the result that we are using here. But again, don't worry too much if you don't follow that. All that we need is that X transpose X and X have the same rank. As I established, the shape of X transpose X is P plus 1 by P plus 1. That means the maximum possible rank of X transpose X is P plus 1, because the rank is the number of linearly independent rows or columns. And so, the maximum number of linearly independent columns, let's say, is the total number of columns, which is P plus 1. And so the maximum possible rank of X transpose X is P plus 1. But the rank of X transpose X is only P plus 1 if the rank of X is also P plus 1, because they have the same rank. That means X transpose X is invertible if and only if X has full column rank or has rank P plus 1. Another way of putting this a little less cryptically is that a unique solution exists for the optimal parameter vector theta if and only if all columns of our design matrix X are linearly independent. And so that's a big result, and you need to remember that. So you may be wondering, in what scenario is it possible that our design matrix X doesn't have full column rank? One scenario is if we have some features that are linear combinations of other features. If this happens, it is not the case that all of the columns in our design matrix are linearly independent, because you can write at least one of the columns as a linear combination of other columns, and that sort of violates the property of columns being linearly independent. So for example, if width, height, and perimeter are all features that we are using, and they're all columns in our design matrix will not have full rank, right? Because you can write perimeter as 2 times width plus 2 times height, which is a linear combination of width and height. So that's one scenario to look out for, and this will be quite prevalent when we discuss one-hot encoding in the feature engineering lecture. The other scenario in which our design matrix will not have full column rank is when it has more columns than rows. And a not so nice term that is used to describe such a matrix is that it's fat, because it's wider, it has more columns than it has rows. Now, in the normal setting, this is not very common because we typically have far more observations, n, than we have features, p plus 1. But if for whatever reason you don't have that much data or you have many features and you find yourself in this scenario, your design matrix cannot possibly have full column rank. The reason for that is because, the rank of a matrix is defined as being the number of linearly independent rows or columns. And so the maximum possible rank of a matrix is the smaller of the number of rows it has and the number of columns it has. And so if we have fewer rows than columns, the maximum possible rank of our matrix is the number of rows, but by definition then that is less than the number of columns we have, and so the maximum column rank of the matrix is less than the total number of columns. And so the rank of our matrix, which again is the same as its column rank, will not be p plus 1, and so the rank of x transpose x won't be p plus 1, and so it won't be invertible. So these are scenarios to watch out for. Let's quickly summarize all of the ideas we've talked about today and provide a roadmap of what we're going to study next. So we defined the multiple linear regression model in terms of a matrix vector multiplication. Our prediction vector, or predicted response vector, y hat, is the product of our design matrix x and our parameter vector theta. We use the geometric argument to solve for the optimal parameter vector that minimized average squared loss, and that was x transpose x inverse x transpose y. Another name for this term is the least squares estimate. It is an estimate because we learned its value from the data, and least squares because it is the value that minimized the sort of average square of the residuals. Speaking of residuals, we also discussed them and their properties, both in terms of residual plots and also the properties that you gain by having an intercept term in your design matrix. And lastly, we talked about when a unique solution for the optimal parameter vector theta exists and when a unique solution does not exist. So I like to think of this lecture as being the third in a trilogy of lectures that sort of establish the foundation of modeling and linear regression. And from here, we are going to look at several variations and extensions to this idea of linear regression, but it will sort of all come back to this lecture. But that's it for this time.